Hi there! Ever built an op-amp circuit, powered it up, and instead of a clean signal, you get a wild, unwanted oscillation? It's a common and frustrating problem for many electronics enthusiasts. Today, we're going to dive into why your op-amp circuit might be oscillating and how to understand this tricky behavior. So, why does an op-amp, designed to amplify or process signals, sometimes turn into an unwanted signal generator? The core reason often lies in the feedback loop. Op-amps typically use negative feedback for stable operation. This means a portion of the output signal is fed back to the inverting input, which helps stabilize the gain and reduce distortion. However, if this negative feedback somehow turns into positive feedback at a certain frequency, your circuit will oscillate. This transformation from negative to positive feedback happens due to phase shift. Every component in a circuit, including the op-amp itself, introduces some amount of phase delay or shift to the signal as it passes through. As the frequency of the signal increases, this phase shift also increases. If the total phase shift around the entire feedback loop reaches 360 degrees, or 0 degrees, effectively, at the same frequency where the gain of the loop is 1 or greater, then the circuit will happily sustain its own output, creating an oscillation. This is known as the Barkhausen criterion for oscillation. Let's break down some common culprits. One major cause is simply the op-amp's internal characteristics. All op-amps have a finite bandwidth and internal compensation. Some op-amps are not unity gain stable. This means they are designed to be stable only when used with a certain minimum gain, for example, a gain of 5 or more. If you try to use such an op-amp in a unity gain buffer configuration, it will likely oscillate. Another common issue is driving a capacitive load. Things like long cables, large bypass capacitors, or even the input capacitance of another device can look like a capacitive load to the op-amp. This capacitance can interact with the op-amp's output impedance, creating an additional pole in the frequency response, which adds extra phase shift and pushes the circuit into instability. Proper isolation resistors or compensation networks are often needed here. Poor power supply decoupling is another frequent cause. If your power supply lines aren't adequately bypassed with capacitors close to the op-amp, noise on the power rails can couple into the op-amp, creating unwanted feedback paths and leading to oscillations. Even parasitic elements, like stray capacitance between traces on a circuit board or inductance in long wires, can become significant at higher frequencies, introducing unintended phase shifts and feedback paths that lead to instability. Sometimes, the input signal itself, if it contains very high-frequency noise components, can excite an unstable region of the op-amp. Adding a small low-pass filter at the input can help. Understanding these factors and carefully designing your feedback network, considering component limitations, and ensuring good power supply integrity are key to building stable op-amp circuits. Thank you for watching and learning about op-amp oscillations with me today. If you found this explanation helpful, please consider giving this video a thumbs up and don't forget to subscribe for more electronics insights and troubleshooting tips. See you next time.